Good morning everyone. So welcome to my YouTube channel Maths Patram. So today we are going to see 11th lecture on Riemann integration. So let's start today's session. So theorem, we start with the Coulomb theorem. Let F close interval AB to R be a bounded function and C and C belongs to R such that then F belongs to R A B if and only if F belongs to R A C and F belongs to R C B. It means F is Riemann integrable over A B if and only if F is Riemann integrable over AC and F is Riemann integrable over CB. In this case, we have Riemann integration of F over AB is equal to Riemann integral of F over AC plus Riemann integral of F over CB. Okay, let's prove this theorem. First, assume that F is Riemann integrable over closed interval AB. Okay. Let P1 be a partition of closed interval AC and P2 be a partition of closed interval C. Closed interval C. Okay. P is equal to P1 union P2 is partition of closed interval AB. Okay. Observe that at U P1 F minus L P1 F is less than equal to U PF minus LPF. Okay. Okay. And U P2F minus L P2F is less than equal to UPF minus LPF. These things are always happens. Now, letting known P, letting known P1 tending to 0 and known P2 tending to 0, then known P is equal to known P1 union known P2 also tends to 0. Okay. Okay. So this implies, but F belongs to RAB. We get limit known P tending to 0 UPF minus LPF is equal to 0. So this implies, okay, so when known P tending to 0, known P1 tending to 0, known P2 tending to 0, this known tends to 0, but F belongs to RAB, so we get this is 0. So applying this, what we will get here? We will get so this implies limit known P1 tending to 0 U P1F minus LP1F is equal to 0. And limit known P2 tending to 0 U P2F minus L P2F is equal to 0. Okay. So whenever this limit tends to 0, UPF minus LPF limit tends to 0, then norm tending to 0 of the partition, then in that case, functions are Riemann integrable over that interval. Okay. So this implies, now by Riemann integration, lecture 8, we have proved this if limit tends to 0, such kind of partition is tending to non-tending to 0, this UPF minus LPF limit tending to 0, then functions are Riemann integrable over that interval of which we are taking partition. So this implies we get what we get, f belongs to R A C and f belongs to R C B. Okay. Okay, so functions are Riemann integrable over A and C. Okay. Now, conversely, assume that f belongs to R A C and f belongs to R C B. Okay. Okay. Now, f belongs to R A C implies given okay. So let epsilon greater than 0. Okay. Since f belongs to R A C implies there exists delta greater than 0 such that for any partition P1 of closed interval AC, we have U P1F minus L P1F is less than epsilon by 2. Okay. Okay. And and any partition P2 of closed interval CB, we have CB U P2 F minus L P2 F less than epsilon by 2. Okay. Now, for P is equal to P1 union P2, we have now P1 union P2 is a partition of closed interval of AB. We have the UPF will be equal to UP of this is equal to UP1F plus UP2F. Okay, and LPF is always less than. Okay. But this LPF will be equal to LP1F plus LP2F. Okay. So this implies UPF minus LPF is always less than okay. UP1F minus LP1F plus UP2F minus LP2F. But this is less than epsilon by this is less than epsilon by 2. So this implies UPF minus LPF less than epsilon. So there exists a partition. There exists a partition P of closed interval B such that UPF minus LPF is less than epsilon by theorem 2 in Riemann integration lecture 8. We have F belongs to R. Okay. Okay. So it is done. Now integral part is remaining. So let's say this theorem. Sorry, this equation star. Okay. Now we have to show that this integral a to b fx dx is equal to a to c fx dx plus c to b fx dx. We have to show this. Let epsilon greater than 0. Okay. By by Darboux theorem by Darboux theorem by Darboux theorem by Darboux theorem there exists delta greater than 0 such that for any partition P1 of AB with norm P1 less than delta, we have U P1F is less than A to B fx dx plus epsilon by 2. Because we are taking partition P1 of AC here. So C will become here. Because F is Riemann integrable over closed interval AC. Okay. And LP1F is greater than A to C fx and dx minus epsilon by. Okay. Let's say this one. Similarly, there exists for any partition P2 of CB with non P2 less than delta, we have we have U P to F is still less than C to B Fx dx plus epsilon by 2. Okay, and L P to F is greater than C to B Fx dx minus epsilon by 2. So let this equation number 2. Okay. So from star 1 and 2, what we have? For P is equal to P1 union P2, partition of AB. Okay. Partition of AB from star 1 and 2, we have LP1 F less than UPF. This is less than UP1F plus UP2F, and this is less than LP1F plus LP2F. Okay. So what we will have? Because this part is less than, so this implies A to B Fx dx minus epsilon by 2, because this part is less than this, and this part is also less than this. This part is less than C, and this A to C integral. And this part is less than C to B integral. Okay. C to B Fx dx minus epsilon by 4. And this is greater LPF UPF, and this is less than A to C Fx dx plus epsilon by 2 A C to B Fx dx plus epsilon by 2. Okay. So what do you have? We have, what is this? A to C Fx dx plus C to B Fx dx minus, okay, this is epsilon is here, it's less than LPF UPF. Okay. A to C Fx dx plus C to B Fx dx. Okay. Plus epsilon. But But f is Riemann integrable. But f is also Riemann integrable. So this implies, so f will be in between okay. F is Riemann integrable. So what we will have? But Riemann integral of f a to b fx dx is always lies in between these two. So both we have. This implies a to b fx dx plus c to b fx dx. Here, what is this? This is c minus epsilon is less than a to b fx dx. Okay, and this is less than a to c fx dx plus c to b fx dx minus plus epsilon. Okay. Since epsilon greater than 0 is arbitrary, we get what we get is we get a to c fx dx plus c to b fx dx is less than equal to a to b fx dx less than equal to a to c fx dx plus c to b fx dx. No, integral over ab is less than this quantity. Is less than this quantity. Okay. And this integral is less than this quantity. Okay. Integral over AB is greater than equal to this quantity and less than equal to same quantity. So what does it mean? It means they are equal. Okay. It means they are equal. Okay. So theorem is proved. Okay. Now, we would like to prove one proposition. We will use this proposition in next lecture. Okay. So proposition. Let f closed interval a b to r be a bounded function. Okay. Such that fx is greater than 0, greater than equal to for all x belongs to closed interval a b. Okay. then the lower integral a to b fx dx is always greater than equal to 0. Proof. F belongs to closed interval a b such that fx is non-negative for all x belongs to closed interval a b. It means this implies mi, small mi, this implies for any partition b is equal to a x naught x1 xn b mi is greater than equal to 0 for I is equal to, so we have f x greater than for all x belongs to xi minus 1 to xi I goes to 1 to up to n. Okay. So this implies small mi is greater than equal to 0 or I goes to 1 to n. So if we multiply both the sides, I goes to 1 to n. Since delta xi is equal to xi minus xi minus 1. Okay. That is non-negative. Okay. This is xi minus 1. So this implies summation I goes to 1 to n mi delta xi greater than this. What is this? This is nothing but LPF. So this implies for any partition P of AB. So this implies lower integral is equal to supremum of LPF. P is a partition of closed interval. Now each member is non-negative. It means this supremum will be greater than equal to 0. So this implies A to B so this is closed. Now corollary. We are saying this proposition 1, okay? Proposition 1. Okay. So remark let f close interval AB to R be a bounded function such that fx greater than equal to 0 for all x belongs to closed interval AB. Then a to b fx dx. Upper integral is always greater than lower integral. So this is non-negative. So we have derivation. Upper integral will be greater than lower integral. Lower integral will be also non-negative because lower integral is non-negative. Okay. So this is bounded function. So proposition 2. Let f close interval AB to R be a bounded function if f is Riemann integrable. So this function is f is bounded function such that fx is non-negative for all x belongs to closed interval AB. Okay. If f belongs to RAB, it means f is Riemann integrable, then the integral of a to b fx dx is greater than equal to 0. So it is simple. Okay. To prove it, it is simple, easy. Since f close interval AB to R is bounded function such that fx is non-negative for all x belongs to closed interval AB. Okay. So by proposition 1, we have lower integral fx dx is greater than equal to 0. But f is Riemann integrable over AB. We have this integral a to b fx dx is equal to upper integral and this is equal to lower integral. Then function is called Riemann integral. So this is given that function is Riemann integral. But this is non-negative. But this lower integral is non-negative by proposition. So this implies a to b fx dx is greater than or equal to 0. Okay. So now corollary. Let f and g close interval a b to r be bounded be bounded functions such that fx is greater than gx for all x belongs to closed interval a b. Okay. If f and g are Riemann integrable, then a to b fx dx is always greater than a to b integral gx dx. Okay. Let's see its proof. Since f and g close interval a b to r are bounded functions, such that fx is equal to gx for all x belongs to closed interval a b, we get f minus g closed interval a b to r is also bounded and fx minus gx and f minus gx is equal to fx minus gx is greater than equal to 0 for all x belongs to closed interval a b. Okay. By proposition 2, by proposition 2, we have integral a to b f minus g x dx is non-negative. But this is equal to what? A to b fx dx minus a to b gx dx. Okay. What is this? So let me write it properly. What is this? A to B F plus minus G X dx. Okay. We know that if F1, F2 are Riemann integrable, A to B F1 plus F2 dx is equal to A to B F1 dx where is x. Okay, plus A to B F2 x dx. Okay, and for any alpha belongs to R, integral A to B alpha F1 dx x dx is equal to alpha times A to B F1 x dx. This result we have proved already. Okay, so we'll apply these things here. So I can write this A to B Fx dx plus A to B minus G F dx greater than equal to 0. No, alpha is my minus 1 here, so it will come out. Okay, now you solve this. You bring this integral minus A to B gx right hand side. Okay, so this implies A to B Fx dx is greater than equal to A to B gx dx. Okay. Okay, so what we have used, so we have done it. Actually, I'm writing in note. Okay. Okay. If F1 and F2 are Riemann integral, we also have this one. We have used this one directly. Okay. We use directly this one. Okay. F2 F3. Using this directly, we have explained it and we have done it. Okay. So we can write directly from here A to B integral, A to B F integral minus A to B G integral, and we can bring minus A to B G integral right hand side, and we are done. So this proposition is also done. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Thank you very much for today's lecture. Like, share, comment, and subscribe my YouTube channel. Thank you very much. We will see you in next lecture.